Hey there, Jeep divers. Ready for a deep dive that's going to make you rethink your sense of smell?
Buckle up.
We're going deep into quantum smell.
Yeah. Exploring the mind-blowing possibility that our noses are actually picking up on quantum mechanics.
Seriously. And to break it down, we've got 5 fascinating factoids to unpack.
5.
5.
All right, hit me with them.
Okay, so we're talking about shape versus vibration in the quantum theory of olfaction.
Right.
Electron tunneling.
Okay.
The isotope effect, and how heavy hydrogen changes smell perception.
Uh-huh.
The musk mystery, where similar structures have wildly different scents.
Yeah.
And finally, the role of quantum biology in unlocking the molecular puzzle of smell.
This is going to be good.
I know, right? So let's jump right in.
Let's do it.
You know, I remember learning in school that our noses detect molecules based on their shape,
Yeah.
like a lock and key.
The classic lock and key model.
Exactly. But how does this quantum theory of olfaction shake things up?
Well, it's true that the lock and key model is a great starting point. The idea that the shape of an odor molecule has to fit perfectly into a receptor to trigger a smell signal.
Right.
But recent research suggests that it might not just be about the shape.
Really?
Yeah, it could also be about the vibrations of the molecule.
Vibrations.
Each molecule vibrates at a specific frequency,
Like a fingerprint.
exactly like a unique fingerprint. And some scientists believe our olfactory receptors might actually be sensitive to these quantum vibrations.
So are you saying our noses are acting like tiny tuning forks? Picking up on these molecular vibes?
Kinda.
That's wild. But how does that even work?
That's the million-dollar question.
I bet.
This is where we venture into the realm of quantum biology,
Ooh, quantum biology.
where the rules of the quantum world, like wave-particle duality and energy quantization, could be playing out right there in our noses.
No way.
Some theories suggest that the vibrational energy of the molecule might be transferred to the receptor through a process called resonance,
Resonance.
and this could be what triggers the signal.
So that's how our noses detect the smell. Through resonance.
Potentially.
Okay, so does this mean the traditional shape theory is completely wrong then?
Not necessarily. It's not about one being right and the other wrong.
Okay,
It's more like we're adding another layer of complexity to how smell works.
I see.
Think of it this way. The shape of the molecule might determine whether it can even interact with the receptor at all.
Like the key fitting into the lock.
Exactly. But then the specific vibrations of the molecule, its unique quantum signature, could determine the strength and quality of the signal.
So it's like the shape gets the molecule in the door, but the vibrations are what really get the party started.
You got it. It adds a whole new dimension to how we perceive smells.
Okay, that makes a lot more sense. Now let's move on to factoid number 2, electron tunneling.
All right, let's get trippy.
This is where it gets really mind-boggling for me. How does this quantum phenomenon, usually reserved for like subatomic particles, apply to something as everyday as smell?
Right. It's pretty wild. So essentially, electron tunneling in the context of smell proposes that electrons can jump between the odor molecule and the receptor, even if they're not physically touching.
Well, hold on. So like a tiny electron hopping across a gap?
Exactly. Defying the classical laws of physics.
That's insane.
And this transfer of electrons could be the spark that ignites the smell signal.
So instead of a physical interaction, we're talking about an exchange of electrons at the quantum level.
You got it.
And the smell isn't triggered until this electron handshake happens.
That's the hypothesis, and there's growing evidence to support it.
Really? Like what?
Well, researchers have found that certain odor molecules that are really good at donating or accepting electrons also tend to evoke stronger smells.
Well, interesting.
So this suggests that electron tunneling could be key in how our olfactory receptors read the information in these molecules.
Okay, I'm starting to see how these quantum concepts are really challenging our traditional view of smell. Let's move on to factoid number 3. This one involves heavy hydrogen and something called the isotope effect.
Isotopes.
Yeah, can you break down what this means and how it impacts our sense of smell?
Sure. So isotopes are basically different versions of the same element,
Okay.
like hydrogen.
Okay.
They have the same number of protons, but a different number of neutrons.
Right.
Chemically, they behave almost identically, but their mass is slightly different.
So slightly heavier hydrogen.
Exactly. And this mass difference can actually change the vibrational frequencies of a molecule.
Ah. And since we're talking about quantum smell, those subtle shifts in vibrations could be detectable by our noses?
Precisely.
Wait, so you're saying that simply swapping out regular hydrogen for this heavier version could change how something smells, even though chemically they're almost the same?
Yep. Researchers actually did experiments where they created deuterated versions of familiar odor molecules.
Deuterated.
Yeah, basically replacing some of the hydrogens with deuterium, the heavier hydrogen.
Okay.
And guess what?
Hmm.
People could actually perceive a difference in the smell, even though chemically the molecules were nearly identical.
Hold on. So our noses are picking up on these tiny quantum differences.
It seems so.
Our olfactory receptors aren't just recognizing shapes, they're sensing these subtle vibrational shifts at a quantum level.
That's what the research suggests.
That is wild.
It is pretty amazing, right? This gives further evidence that quantum phenomena might be more involved in our sense of smell than we ever thought.
I'm with you there.
And it opens up some fascinating new avenues for research.
Like what?
Well, for example, if we can understand how these subtle isotopic differences translate into different smell perceptions, we might be able to design entirely new fragrances.
Whoa. New perfumes based on quantum mechanics.
Exactly, by manipulating the vibrational frequencies of molecules.
Okay, my mind is officially blown. This is seriously making me rethink everything I thought I knew about how our noses work, and we've still got 2 more factoids to go.
I know, right? Buckle up. This deep dive is just getting started. Yeah, this deep dive is full of surprises. Ready for the next one?
Hit me with it.
Okay, so let's talk about the musk mystery.
Musk, as in perfume.
Exactly. Musk is a super popular ingredient in perfumes, but it's always puzzled scientists.
Oh,
Well, there are all these different types of musks with scents ranging from sweet and floral to like earthy and animalistic.
I've noticed that, yeah.
The thing is, musk molecules can have wildly different shapes and chemical compositions.
Really?
Yet they all bind to the same type of receptor in our noses.
That's interesting.
So it's not as simple as the lock and key model would suggest.
Right, because if it were just about shape, then all those different musk molecules shouldn't smell musky.
Exactly. So something else beyond just shape must be at play.
Okay, so what could it be? Could this be another case where quantum mechanics is involved?
It's very possible. One theory is that even though these musk molecules have different structures, they might share some kind of vibrational similarity.
Vibrational similarity.
Yeah, like they're all playing the same musical note, even though they're using different instruments.
So our noses are like sophisticated musical instruments themselves, picking up on these subtle vibrational harmonies.
That's a great way to put it. And that could explain why they all smell musky, even though their shapes are so different.
Wow, that's fascinating. So the quantum theory of olfaction could potentially solve the musk mystery that's been bugging scientists for so long.
It's definitely a promising avenue for research.
I can see that. And speaking of quantum mechanics, what about electron tunneling? Could that also play a role in how we perceive musk?
Definitely a possibility. Remember how we talked about electrons potentially jumping between the odor molecule and the receptor?
Yeah, like an electron handshake.
Exactly. Well, it's possible that the musk receptor is especially sensitive to this exchange of electrons.
So the musky signal is triggered by this quantum handshake.
It's a compelling theory, and it ties in nicely with the quantum theory of olfaction.
This is also mind-blowing. We've gone from shapes fitting into receptors to electrons hopping around and molecules vibrating like tiny instruments.
I know, right? Smell is way more complex than we thought.
It really is. It makes you appreciate how much is happening at the microscopic level just to allow us to experience something as simple as a scent.
Absolutely. And this brings us to our final factoid, quantum biology.
Okay, bring on the grand finale.
Mm-hmm.
What exactly is quantum biology and how does it fit into all of this?
Quantum biology is a relatively new field that explores how quantum mechanics plays a role in living organisms.
So it's like bridging the gap between physics and biology.
Exactly. It's a fascinating intersection that's challenging our understanding of how life works at the most fundamental level.
I can imagine.
Mm-hmm.
So how is quantum biology shedding light on the mysteries of smell?
In a few ways. For one, it's providing a theoretical framework to understand how electron tunneling or molecular vibrations could actually influence the behavior of olfactory receptors.
So it's helping to connect the dots between all these quantum phenomena we've been discussing.
Exactly. And it's also shedding light on the role of something called quantum coherence in smell.
Quantum coherence, what's that?
It's the idea that the odor molecule and the receptor might actually exist in a kind of entangled state.
Entangled, like they're linked together in a way that classical physics can't explain.
You got it. They're sharing information in a way that we're just beginning to understand.
Wow. So smelling a flower isn't just passively receiving information about the world, it's actively engaging with it at a quantum level.
That's a beautiful way to put it. It highlights the fact that our senses are not just passive receivers, but active participants in shaping our perception of reality.
This deep dive has seriously blown my
I
mind.
know, right? Smell is way more complex than we ever imagined.
It really is. Who knew there was so much quantum weirdness going on inside our noses?
Yeah, it makes you wonder what other secrets our senses are hiding.
For real. Before we wrap up, though, I always like to leave our listeners with something to think about.
A little food for thought.
So here's a question. If quantum mechanics can influence our sense of smell, could it also be playing a role in our emotions,
Ooh, that's a good one.
like how we experience the world?
That's a really interesting idea, and it's something that some scientists are starting to explore.
Yeah.
Think about it. Smell is often considered our most emotional sense.
True. Certain scents can, totally transport you back to a specific memory.
Right. And those memories often come with strong emotions attached.
So true. Like the smell of freshly baked cookies always reminds me of my grandma's house.
Oh, that's sweet.
It brings back all these warm, fuzzy feelings.
And if smell is being influenced by quantum mechanics, could it be that those quantum interactions are somehow entangled with our emotions at a deeper level?
Whoa, hold on. So you're suggesting that the way a molecule vibrates, or the way electrons tunnel between a molecule and a receptor, might not only be creating a smell signal, but also shaping our emotional response to that smell.
It's a possibility worth exploring.
That's pretty mind-blowing.
It is, right. We know that quantum mechanics is all about interconnectedness and non-locality.
Right, like the idea that particles can influence each other even across vast distances.
Exactly. So could there be a similar kind of interconnectedness between the quantum world and our inner emotional landscape?
Wow. That would mean our emotional responses to smells aren't just simple chemical reactions happening in the brain.
It would be something much deeper.
A kind of quantum entanglement between our physical senses and our emotions.
That's a really profound thought.
It really is. So every time we smell something,
Mhm.
we're not just experiencing a scent. We're tapping into this hidden world of quantum emotions.
It's a beautiful and mysterious idea.
It really is. I don't think I'll ever be able to smell a flower the same way again.
Me neither. Every scent now seems like a portal to a whole new world.
It's like a secret quantum language speaking to our hearts.
And that's the beauty of science. It constantly challenges us to expand our understanding of the universe and our place within it.
Absolutely. A huge thank you to you for guiding us through this incredible journey into the quantum world of smell.
It was my pleasure. Thanks for having me.
And to all our amazing listeners out there, thank you for joining us on this deep dive into the fascinating intersection of quantum mechanics and our sense of smell. We hope you leave with a newfound appreciation for the complexity and wonder of this incredible sense, and maybe even a few new questions to ponder.
Keep exploring, keep questioning, and never stop being amazed by the world around you.
Until next time, deep divers.